Welcome, everyone, to today's Explainer. We're diving into a genuinely fascinating world today. A world where your car isn't just a vehicle anymore, but an active, vital piece of our entire energy infrastructure. We're going to break down the actual design and simulation of bidirectional AC/DC converters for electric vehicles. It's an absolutely incredible piece of electrical engineering, and it's literally transforming the future of power. Let's get right into it. But before we get into the nitty-gritty of the how, we really need to talk about the why. Vehicle-to-grid technology, or V2G, literally turns electric vehicles into massive mobile batteries. Instead of just pulling power from the wall, they can push it right back out. They can discharge stored energy to stabilize the power grid during peak demand. It's a real game changer. So here's our circuit map for today. We'll start by looking at the potential of vehicle-to-grid, then we'll discuss securing power quality. After that, we'll break down the AC to DC H-bridge, move on to voltage regulation, and finally explore the path back to the grid. All right, Section 1. The potential of vehicle-to-grid. This bidirectional converter is honestly the master key that unlocks so many real-world applications. We're talking about things like regenerative braking to seamlessly capture lost kinetic energy and incredibly efficient energy management right within the vehicle itself. But beyond just the car, it enables full grid-to-vehicle and vehicle-to-grid capabilities. It optimizes how your battery charges to actually extend its lifespan, and it can even act as a mobile emergency power supply during blackouts. Moving on to Section 2, securing power quality. Okay, so now we're shrinking way down to the electron level to track the exact path of the current as it enters from a standard 230-volt AC grid. These are the core LTSpice simulation parameters from the Wired White study. Notice that switching frequency, 20 kilohertz. That isn't just an arbitrary number, it's a highly deliberate trade-off, perfectly engineered to balance the need to reduce total harmonic distortion with the overall energy efficiency of the converter. But even with that perfectly tuned switching frequency, we still absolutely mean protection. Enter the LC input filter. You can think of this kind of like a high-tech water filtration system. See, when the current flows, the converter naturally generates what are essentially turbulent waves. These are high-frequency harmonic currents. The LC filter basically blocks those turbulent waves, preventing them from flowing backward and polluting the main grid supply. It ensures clean, stable power right from the start. Next up, Section 3, AC to DC and the H-bridge. Let's move a little further down our circuit path. The full bridge converter, which engineers often call an H-bridge, has this really beautiful dual nature. It's the ultimate two-way street. During charging, it takes that 230-volt AC sine wave and rectifies it into DC, just by switching diagonally opposite transistors. But when discharging, when we're sending power back to the grid, this exact same component inverts the DC back into AC. The absolutely crucial point here is that to maximize efficiency, these switches commutate right at the line frequency, which vastly minimizes power losses. Now, of course, those transistors don't just switch themselves, right? They are strictly guided by a pulse width modulation, or PWM controller circuit. Operating at a 50% duty cycle, this physical control system uses an op-amp to generate the signal, an OR gate to combine it, an SR latch to hold the state, and an NMOS gate driver to actually physically drive the transistors. This incredibly precise cause and effect management is exactly what ensures perfect synchronization with the grid. So after the H-bridge does its job, what do we actually get? Well, the immediate DC output is what engineers call noisy. According to the LTSpice simulation, it rapidly fluctuates between 397 and 398.5 volts. This ripple is just due to transient effects and switching dynamics. I mean, it is technically DC, but it's absolutely not the clean, smooth DC that our electric vehicle battery demands. Which brings us to Section 4, voltage regulation and the buck-boost converter. So we really need to fix that noisy, rippling voltage and step it up safely for the battery. To clean up the signal, the design uses an interleaved, parallel, bidirectional buck-boost DC-DC converter. Let's bring back our water analogy for a second. If the LC filter was our water purifier, this buck-boost converter is our high-end pressure regulator. It smooths out the flow, drastically minimizing battery current ripple, which, by the way, is absolutely essential for preserving your battery's lifespan. Plus, it enables power factor correction, ensuring the entire system operates with maximum electrical efficiency. And here is the fantastic result of that stage. A stabilized, perfectly smooth DC output sitting continuously at exactly 398.84 volts. This right here is the pristine electrical energy ready to safely charge the 400-volt EV battery. The simulation also provides us with some really precise performance metrics. measuring exactly 7.98253 amperes flowing through resistor R1 in this state. Monitoring this specific current magnitude is a critical metric for the engineers evaluating the overall efficiency of the charger. Let's quickly summarize this entire forward microjourney chronologically so you can easily grasp the complete AC to DC transformation. Step 1, we start with a 230-volt AC input from the grid. Step 2, it gets smoothed and protected by our LC filter. Step 3, the H-bridge rectifies it into DC. Step 4, the buck-boost converter steps up the voltage and cleans up all that ripple. And finally, Step 5, our 400-volt DC battery is successfully charged. All right, final stop, Section 5, the path back to the grid. But as we know, this definitely isn't a one-way street. Let's shift gears and unlock the true magic of this bidirectional circuit by tracing the microjourney entirely backward. The 400-volt stored DC energy leaves the battery. The buck-boost converter now acts as a step-down buck converter, reducing the voltage to a manageable 230 volts DC. That lower DC voltage is then sent right back into the H-bridge, which completely reverses its previous job and inverts the DC perfectly back into AC, synchronized to feed directly into the power grid. Literally, your car is now acting as a backup power plant. Zooming back out to the macro level for a second, we can really see how this LTSpice circuit design links directly to some amazingly transformative real-world applications. It's the literal foundation for V2G distributed energy. It integrates seamlessly with energy storage systems for unpredictable renewables, like solar and wind. It optimizes your car's regenerative braking, and it turns massive fleets of everyday vehicles into emergency mobile power supplies. And all of this brings us to a pretty profound realization. With this bidirectional converter technology, we aren't just changing how we drive, we are changing how human civilization manages and shares power. So I'll leave you with this provocative question to ponder. How will millions of mobile energy storage units parked in driveways all over the world completely reshape the resilience of our future grid infrastructure? Thanks so much for joining me on this explainer today. I really hope this helped you understand the incredible science going on right under the hood.